Thanks for joining today. I'll be talking about CIFAR-10 for DAWNBench and give you a sort of a quick overview as to what DAWNBench is. Quick look at the data set, and then we'll be looking at types of models and the ways that we train these models, so different types of regularization that we can use and the optimizations for the models that we're using for DAWNBench. So starting with DAWNBench itself. So DAWNBench was a competition that was set up by Stanford University. And the coverage of the benchmarks was across 3 different data sets. So they've got computer vision data sets, which are CIFAR-10 and ImageNet, and they've got an NLP data set, which is Squad. And for these tasks, they assign different tasks that you need to do. So for the computer vision, that's image classification. And for the NLP task, that was question answering. And different to the way that research is generally done, where you're looking to obtain the highest level of performance, what DAWNBench did was they set a threshold for near state-of-the-art performance. And then the competition was to get a model that reaches this target as quickly and as cheaply as possible. So they were looking at metrics like training time, and they were looking at training cost, how much it costs to train on different types of instances. And they also did some coverage on inference. So looking at inference latency for a single sample, so how long that takes to go through your model and get scored, and then the inference cost. So slightly different approach to just looking at model performance. And internally, what we tried to do is implement a model that we could do benchmark testing for MXNet. So we weren't entering the competition, we just wanted a near state-of-the-art model so we'd get more reliable tests, rather than just looking at image throughput, because we are interested in reality with model performance. It needs to be good, it needs to be a good model. So CIFAR-10 dataset, 60,000 images in total, 50,000 you have in your training set typically. The images are really small, so it's 32 pixels by 32 pixels, and they're across 10 classes. That's CIFAR-10. This dataset has been around for quite a while. It's been around for about 10 years, and I like to think of it more of the dataset for the people, because it's much more manageable than ImageNet, and you can actually do some interesting research on it. And a lot of the new algorithmic developments have actually come out of research done on CIFAR-10 versus ImageNet. ImageNet, a lot more on how much compute you've got, just put power behind it. So that's why CIFAR-10 was quite a good data set to look at. So this is the final results table for CIFAR-10 on DAWNBench, just closed the end of last month. And huge range of results here. You'll see this is actually the top, 8 results. 8 results. And they range, we've got 3 hours at the bottom all the way to 3 minutes at the top. It's a huge variation, and that was across 50 entries. You'll notice that typically smaller models are the ones higher up because you can train smaller models quicker. They're not going to obtain the true state-of-the-art performance, so they're not going to get above 94%, but they're good enough to reach the target, and that's all that's needed for DAWNBench. So you'll see some ResNet 18s as opposed to further down ResNet 164. So the model that we actually implemented was ResNet 164 for our benchmarks. That's because the newer models, they were just on the last day that they were added to make sure no one could copy their results. And then in the other competitions, so this is where we're looking at the cost to train. So 26 cents to train CIFAR-10 model to 94% validation accuracy. And that was actually on a Paperspace Volta, because their on-demand pricing is cheaper than AWS. It's not as cheap as spot pricing for AWS, but that wasn't allowed to be included as your costs for this entry. And for inference, wasn't really competed much for DAWNBench on CIFAR-10, much more on the ImageNet. So these are just the base models that were submitted by Stanford at the start. So let's have a look at a few of these models, and let's build up from what I like to call the vintage ResNet, all the way back in 2015. And this is a ResNet 18. So this is what the architecture looks like from the highest level. Mm-hmm. Yeah, so you can just. Oh yeah, sorry, yeah. So you're asking about how do you compare the time across different machines? So for DAWNBench, they don't care what machine you use, they're just purely based on time. And they don't look at how much memory that hardware has got or CPU capacity. It's just purely done on time. So you could do a further analysis based on these results and maybe find the optimal combination. But that's why they have the cost factor, because typically cost is then correlated with the performance. So if you want the cheapest, then you'd look at the cost scorings. So the ResNet 18 model typically got lots of convolutional layers, and the way that it's structured is with different stages. So for ResNet 18, there's 4 stages, and each stage has got a different number of channels or filters in your convolutional layers. And here we've got 2 what's called blocks in each stage. So we'll look at that in a little bit more detail. And this is the exact model you'd get if you went to Gluon and went to the model zoo and retrieved ResNet 18 v1. An interesting part of ResNet is at the end where we've got the average pool. So this averages all the values in your feature map across channels. And so this means that you're not totally dependent on the input image spatial dimensions as you would be with some other models. That can vary and it gets averaged down, and then you have the fully connected layer where that's going to give you the classifications of each image. So ResNet 20, you'd think, oh, that would be just a minor modification, maybe extra 2 convolutional layers more. Well, actually, it's completely different. So we've got 3 stages and different number of blocks in each stage, different number of filters. So the difference between these two is because in the original ResNet paper, there was architectures for ImageNet and there was architectures for CIFAR-10, completely different data sets, you need completely different models. So we have to be careful when talking about ResNet and then followed by a number. It's underspecified. You really need to look into your model, see which one's how many blocks, how many filters, etc. And then ResNet 50 would be another one. This is where I think you get a namespace clash between the 2 different types of architectures. So ResNet 50 could mean 2 different models. You really need to look at it. Different number of blocks in each stage. So what does a block look like? Well, typically we've got the basic block. And the idea really behind a ResNet is with these basic blocks. We have, instead of learning a mapping from X to Y, we learn the residual of the mapping from X to Y. So we include the identity function, and then we learn the difference of the identity function instead of the whole mapping. And where this came about was when, in the old style deep neural networks, as you increase the depth of your network, the performance of your model would deteriorate. And the model has the capability to learn an identity function, so it wasn't learning the identity function. And so by adding this, this knowledge of starting with an identity function and just learning the residual, that helped the model scale and get deeper and deeper and deeper. So a basic block has just got 2 convolutional filters with the same convolutional layers with the same amount of filters. And a bottleneck block has a slight compression at the start of the block. So you'll notice that the 2 convolutional layers are of a quarter number of filters to the last convolutional layer. And typically you would use a bottleneck block for a larger data set than you would a basic block. So for CIFAR-10 models, you see a lot more of the basic block. And these are both implemented in MXNet. And you'll see the paths to those. The next development that came along was the pre-activation residual block. So in the original basic block, the ReLU was actually applied on the information path, so it was applied after the addition. And so it's not too much of an effect, but it's actually being applied every time you use a block over and over and over again. So if we move the ReLU into the branch, then we've got a clear path of information through that's not going to be hindered in any way. And that's called the pre-activation block, because the pre-activation is being passed down the information channel rather than the post-activation, which you'd see on the original block. And, yeah, question?
How do you deal with a shape mismatch between the input and the output, or is there no shape mismatch?
So for a typical block, there wouldn't be a shape mismatch. So if we're looking at the bottleneck, we're along the information channel, we've always got 64 filters in the same space. But when you move between stages of the ResNet, if we go back here, you'll see stage 1 has a different number of filters to stage 2. The first block in each stage is responsible for downscaling the image and increasing the number of channels. So it's the first block that is responsible for that, and then any successive blocks don't change the scaling. And I've just written the feature map sizes below each stage, so you can see how that's changing. And then after the pre-activation blocks, we got wide blocks. So these are really simple. This is just increasing the number of channels that you've got in your block. So it's wide with respect to the original ResNets that were proposed in the paper. So you would take the ResNet 18 architecture and you could scale up the number of filters in each stage by a given amount. So K is the widening factor, and you'd scale the number of channels by this K. And the research that was done when the wide blocks were suggested was that widening the network has a better performance for the same number of computations than depth. So it was better to widen your network rather than make it deeper. And wide residual networks were the ones that you'd see at the top of the leaderboard. So we had the wide ResNet 22, I think, and that was using wider residual blocks, more filters. And then we've got a few variants on ResNets. We've got PyramidNet, which, going back to your question, Thomas, is how the reshaping is done. And between each stage, previously we had a big jump in the number of filters. We double the number of filters. And that actually has a detrimental effect on the model. So instead of increasing it in large jumps, we'd have more stages with more incremental increases. So it's much, much smoother. So this is flipped of the diagram that I showed you before as we go from input to output, where you've got many more stages, smaller changes. And I think the idea from this came from an analysis done on removing different layers from models. So it was done on a VGG16 model, and if you take a layer out of a VGG16 model, it's going to affect the performance a huge amount. For ResNets, it was found it doesn't make too much difference for a typical layer or typical block of ResNet, because ResNet acts somewhat like an ensemble. You've got the information path through the middle, but you've got all these shallow models that are operating. So if you take one out, it doesn't affect the performance overall. But it did matter if you took one of the first blocks of each stage, which is responsible for changing the amount of channels and doing the reshaping. That was really important. So to reduce the impact of these specific blocks, you could have a lot more of them, and that was the idea proposed with PyramidNet. We've also got ResNext. So instead of having one branch, you can have lots of branches, and you could have smaller convolutional filters. So instead of 64 filters, you could have lots of branches with 4 filters. And this builds on that ensemble idea. So now we've got even more models learning different features, and we can combine them together. And DenseNet was an idea where you take the feature maps, or for every layer, you give it all the preceding feature maps concatenated together. So as you progress through this dense block, you create a very dense network of the feature maps. And you see from the diagram, the last layer has all the preceding feature maps. Okay, let's move on to regularization.
With DenseNet, how do you deal with the spatial resolution difference?
So for a given block, the spatial dimension is the same. So this would be...
But this is the same block?
Same stage, sorry. This is equivalent to the stage. And you would then have another stage very similar, but it wouldn't have connections with different stages. You only combine within a given stage. Yeah. And the first layer would be responsible for the changing spatial dimension.
Would you like to explain what I'm going to ask? And assume that, can you like roughly characterize the differences of based on some for example, ResNet is very good at some types of
So you're asking what types of ResNet is good for different types of tasks potentially.
What are that?
So at the moment, the state of the art is looking towards ResNext. These ideas have built on top of each other a little bit more. So you're going to add complexity as you bring in more of these different types of connections. So if you're looking for a simpler data set, you might not want to be too complex with your model. You might want to stick to more of the standard ResNets. And so we saw from the DAWNBench findings, at least, that it was a relatively simple model that came top, and that was just a wide pre-activation residual network, rather than looking at DenseNets and ResNext models. But you'd see some of these models on the ImageNet competitions. So I think it's a factor of the data size as well. So regularization, something that's really, really important with smaller data sets as well, because we've got models with huge amount of capacity. We've got only 50,000 32 by 32 images, so it's quite a small data set. So we've got the typical suspects, weight decay, something that we need in our model. So that's going to bring the weights of your model closer and closer to zero progressively over time. So that's something we need to be doing. Data augmentation, there's just a standard technique that seems to be used for CIFAR-10, which is just to add some padding, 4 pixels either side, and then do a crop. Typically, the padding was done with just black pixels, but it seems to help with the regularization. And so our input image would look something like the image on the bottom. We want to flip and normalize channel-wise. We've also got different other parts of the network that are going to implicitly help with regularization. So we've got batch norm, because the batch norm is taking a batch and working out what the mean and the variance should be. That's just a sample. That has some noise. That's going to bring in noise that helps with regularization. Similarly, just taking a small batch helps with regularization. And there's some research done on learning rate that we'll talk about later. That means if you have a high learning rate, that also has a regularizing effect. More noise, and you're exaggerating that noise. So all of these help with regularization. These are standard methods. And there was a few more novel methods that were introduced recently, and a few DAWNBench submissions had them. So we've got random erasing, which is just to take random parts of your input image and block them out and fill them with just random noise or a constant value. There was a model, or an idea that came out of Facebook AI research. Oh, got a question?
Sorry, I missed it. These transformations that are during your time count for training, or they're before?
These get included in your time, in the amount of time that you're recording for training. Yeah, it should be end-to-end, and includes loading your data as well. You kind of preloaded data.
How small batch size helps? Smaller batch size make it more regularized?
So the question is, does a smaller batch size help with regularization? Yes, it does, and to a point. It's because the images that you get, there's more variation overall for a smaller batch size. If you've got a bigger batch size, the gradients will get averaged out, and you won't get the same amount of noise in your gradient estimates. So typically for CIFAR-10, the right batch size to use is around about 128. That was typically found to be one of the best. And we'll see later on as well some other effects of batch size. So Mixup, gonna kind of want to go through this one a bit quicker, just make up some time. Strange idea, but it's combining input samples and doing a linear interpolation between 2 input samples. So for images, that would give you an image just like this. We've got part of a ship and part of a deer. And so we're getting some really interesting input image. We'd have to change the label as well. So now the label has to be a combination of a deer and a ship. So we can't just combine labels if we've got deer as class 1 and ship as class 3, because that would average out to be 2, which makes no sense because that's a different class. So we have to make sure we one-hot encode the labels first and then do the combination. And the proportion that we combine the 2 input samples is we sample from a beta distribution. So a beta distribution would look something like this. And depending on what we choose as the parameter for the beta distribution, we might sample lambdas that are close to the center, which would be 0.5. We used alpha of 2, and that would be like the image we see, a pretty equal combination of the two inputs. Or we could use alpha that's less than 1, and then we're much more likely to sample a lambda closer to 0 or closer to 1. So then the input would be much more like one image or the other. So why does this work? Well, the idea was to bring in a prior that we want to have a linear interpolation, or we want the model to behave linearly between the training classes. And so this reduces undesirable oscillations between classes, and really good for regularization and generalization of your model. Because for points that are just outside of the training set, without doing this kind of regularization, there might be crazy variations in what your models learn, and these oscillations don't help. And it's also found to limit the memorization of the data set and help with adversarial examples too. This was just implementation. Instead of choosing 2 random samples in your whole data set, you can do the mix-up just on a batch. And this was applying it per batch. Right, lastly, optimization. So we've looked at the models, we've looked at how to regularize, and now how do we actually do the optimization. So one technique that has been used for the CIFAR-10 DAWNBench challenge was starting with a learning rate finder. So learning rate was found to be the most significant hyperparameter. It's the biggest effect, so choosing it wisely is a good thing to do. And the idea with a learning rate finder is you do this before your training, so it's a pre-training step, and you start with a really, really small learning rate, and you slowly increase it batch at a time. And you update your model using this learning rate that is increasing over time, and you want to plot your loss as you're increasing your learning rate. So see here, we start with a really small learning rate. Our accuracy is really low. Because the learning rate's really small, the model's not really updating. Up until a point where we see 0.05, then the model starts to learn. So this is looking good. But then we set the learning rate to about 0.015. That gets slightly too high at this point, and the accuracy then starts to fall. So we want to select a learning rate within these ranges. We don't want to set the learning rate any higher than 0.015. And so I tried this on the ResNet 164 model that I was using, and just derived a learning rate. And that actually lined up with the learning rate that I had found just by lots of hand tuning. And this is much quicker to do than sending off a whole run that's going to take 2 hours and then just changing a learning rate. This is done really, really quickly because you're applying it batch at a time instead of epoch at a time and doing the whole training run. So a learning rate schedule that's typically used would look something like this. So we've got decay, and we can add warm-up. So we want to start the learning with a relatively small learning rate for a few number of epochs, maybe 5 epochs, then increase it up to our starting learning rate, and then drop periodically. And typically it's a 1/10 you'd drop it by. Well, you drop it to a 1/10 of the value. And then you'd get a learning curve that looks something like on the right-hand side, and you'd see these steps. And that's relatively standard. But then new method that was introduced actually in 2015 was cyclical learning rates. So we're going to, instead of start with a learning rate high and periodically reduce it, we're going to find a lower bound and an upper bound for the learning rate and oscillate between the two at a given frequency. So here the frequency we'll be looking at is a step size of 5 epochs. And what effect does this have? Well, we can see that we can reach a higher validation accuracy much quicker. And we reach lots of different minima, or at least that's what the theory is behind. Every point that we reach at the peak of the validation accuracy could potentially be a different local minimum. And the reason why this could work is because we're decreasing the learning rates much more smoothly. We don't take a big step. So we can find a much flatter local minimum, which generalizes better. If we just reduce the learning rate in a huge step, we might fall into a ravine, and we're relying very, very heavily on where the model is just at the point where the learning rate changes. But if we decrease the learning rate smoothly or linearly, then we're not going to have that same effect. We're going to, or at least it was suggested, that we're going to find a flatter local minimum. Building off what we can do with cyclical learning rates and each point of when the validation accuracy is high, when the learning rate is really low, we can take a different model. So that was the idea with snapshot ensembles. So this is great because we can train one model. We have one training pass, but we get n models out. So m being the number of peaks that we get in validation accuracy. We can take those as separate models and then ensemble them together. So if this was the loss surface, you could see that with a standard LR schedule, we might go and skip around the peaks in your loss surface and you'd get to one model that we could use. But with cyclical learning rate, we're going to be oscillating more, we're going to be finding more different local minimums that then we can combine. So that was quite an interesting technique that was used. And lastly, this was the technique that was used to win the competition. So it's a more extreme case of cyclical learning rates where you only have one single cycle. And your higher bound for your learning rate is much greater than was used before. So with the same learning rate finder plot, we would have typically stopped the learning rate where we said the learning rate should be no higher than 0.5. But if we carry on and keep increasing the learning rate, we see the test accuracy does start to fall, but it doesn't fall that much. It doesn't fall too significantly. So we can still pick a learning rate in those ranges, and although it won't be, we're not going to reach the perfect test accuracy straight away, it's not going to hinder the model a huge amount. So they did a similar analysis with the ResNet 56 and picked learning rates from 0 to 3. We do one step, so we increase from approximately 0 to 3 and back down again. And then we have a second stage of the learning rate schedule where the learning rate goes from a very small value back down to 0 across the same amount of time. And that was called the one cycle learning rate schedule.
And just to confirm, the learning rate across a single epoch, does it change across epoch as well, or you keep it the same as the epoch?
So it's actually advised to keep it moving within an epoch. So you change it every single iteration, every single batch. And that creates an even smoother schedule rather than having steps on every epoch.
And that's what they did here.
And that's what they did, yeah. And so using this learning rate schedule, they were able to train this model an order of magnitude quicker. So we've got one iteration instead of 8,000 iterations. And we could reach a greater validation accuracy as well. So this was the technique that won.
So they use that plot over there to try to pick what is the interval between learning rates.
Yeah.
And how do you pick like how long it should be until you can come back down? Like in there is like 20 epochs. Like why not 10 or 30 or 40?
I think this was a hyperparameter they investigated and tried to tune. And that's called the step size. You typically try and make it as small as possible if you wanted to do super convergence. You just need the smallest step size possible to reach the level of accuracy that you're after. And in that case, it was 94. I tried to use this, and for my model, I couldn't reach 94% accuracy, but I reached similar to what they'd got in the paper. But the guys at Fast AI have done it on a different model, and they've reached 94%, and that's what they submitted.
So those numbers are plot over there.
That was from the paper, original paper, but I've been able to reproduce those, but not obtain 94% with that model.
Oh, so they haven't released their model.
So Fast AI have released their model as well, yeah, and they were using this technique with a wide ResNet, and I haven't done this on the wide ResNet. And this is just to say, yeah, use fast learning rates. It seemed to help in this case. Very, very sensitive to the data set that you're using and the model that you've chosen. and that was a finding. So I think there was some reviews done on the paper. It wasn't accepted into conferences because it was hard to reproduce on other data sets and different models. So mileage may vary. For CIFAR-10, this worked really well. And even if you don't get super convergence, typically you'd get an increase in your training speed by using cyclical learning rates. It's just not as a pronounced an effect. You might get half the training time, which is still pretty significant. Last slide here is just looking at batch size. So this is something that I found, just something to be aware of. If you increase your batch size significantly to have more efficient computation, you do need to change your other hyperparameters as well. So not only do you need to scale your learning rate, typically by the same factor that you've increased your batch size, but other things will need to change as well. So this was for ResNet 18. I increased my batch size quite significantly from 64 to over 2,000. And without changing any other hyperparameters apart from that learning rate, there was a 3% difference in the error rate, in the validation error rate. So this could be due to the effect of regularization from smaller batch sizes. And there was some research done by Facebook when they were training ImageNet in under an hour. And they advised that the very first few steps of training are very important. And you should have a linear warm-up in your learning rate. So links back to what was found with the cyclical learning rate schedule. It's a more simple version of that. So if we added warm-up into this, we could expect the difference to come down. And typically the effect isn't anywhere near as big as 3%, but it's still significant if you're looking at state-of-the-art models and you need to reach a certain given threshold. All right, thanks.